So Amal is from University Côte d'Azur also in France, and I think it's a continuation of the last talk. So Amal, please start with your talk and maybe give a short introduction also of you.
Okay. So, good afternoon. I am Amal Ben. I'm a research and development engineer at the Laboratory of Electronic Antenna and Telecommunication, Sophia Antipolis, France, so the LEAT laboratory, as Antonio was talking about. And today I will present our work done in collaboration with NXP Semiconductors Mougins, France, so in the context of the PhD project of Antonio Genov, which is author of this paper also. So the subject of this talk is timing-aware high-level power estimation of industrial interconnect module. And as you may guess, we will talk about power estimation and management at high level of abstraction. And the architecture under test will be an NXP interconnect module. So the outline of my presentation is the following. I will shortly introduce the context of our work. Then I will present PowerClock-ARC library, which is the solution used to manage power dissipation in our work. Next, I will move to the design under test, so to describe the functional model and the test bench, followed by some simulation results and the power correlation with silicon measurement. So SoC performance metric is changing, moving from pure performance to performance efficiency and minimum power consumption. This new metric is already crucial for IoT or mobile devices. It's becoming key for various applications like automotive, embedded, or space. So in this work, we study how to manage and estimate those metrics together at early stage of the design flow and more precisely at transactional level. In our case, we will use AT model from System C using PowerClock-ARC library, which I will present in the next slide. This study is done on System C TLM model of NXP AMX8 QuadMax SoC subsystem, and we enhance the power model and the functional model of the two external memories using an open source tool which is called the DRAM Power Tool. So the LEAT has implemented PowerClock-ARC library, which is a C++ System C TLM library for power management integration on System C TLM-based models. We see on the picture the classes implemented in the library like power domain, supply net, power switch, inspired from the UPF standard. Here I talk about the yellow blocks. And but we see also other classes like clock domain, clock manager, DPLL for clock tree control and modeling, which are the yellow box. So if you have attended the presentation of Antonio Genov, then you may be a little bit familiar with PowerClock-ARC library. And if not, please have a look of the slides for more details. So in this slide, I will present the methodology of PowerClock-ARC, which is basically composed from 4 steps. So starting by the power and the clock intent specification, in which we break down the system into different power and clock domains, and we define the structure of the power model. Then we have the PME modeling stage, which is the block System C TLM used for connecting the functional model to the power model. And at the end, we have a full power-aware simulation that generates power curves. And the 4th step is a perpendicular step. The purpose of this step is to check actually the clock and the voltage management properties during the simulation. And when a contract is violated, an error which is implemented as an exception is triggered. For example, when the functional model runs instructions on a block which is clock gated, an error should be generated. For separation of concerns between HDL design and power clock intent, the specification of power clock intent is built above the design element object, which is a reference to a module in the System C design model. So on the picture here, we see the code related to the power model should be inserted in the code for the functional model that serves to make the connection between the design element and the corresponding functional module. And every time there is a state change, there is an update on power computation done on the design element level and then moved up to the platform level. Thus, at the end of the simulation, we obtain the power consumed per module, per clock domain, per power domain, etc., but also the total power of the whole of the entire platform. So let's move to the design under test. So to evaluate the power clock arc methodology, we use NXP AMX8 QuadMax SoC, which is a member of AMX8 series. This processor is developed for automotive and industrial application and contains a variety of digital and analog modules, such as core processing unit clusters, graphic processing units, video processing units, display controller, and other advanced features. There is one subsystem which we call switch matrix, and which will be the main object in this study. The switch matrix is provide the connection between about 15 subsystems and 2 external memory DRAMs. So the switch matrix is a highly granular interconnection module with multiple quality of service and routing algorithm. So this model contains multiple blocks, and each block serves to translate, treat, isolate, or schedule specific transaction or entire burst of transaction. The internal application of several quality of service algorithm enables the prioritization of certain subsystem traffic and contributes to the optimization of the performance and memory usage. The entire switch matrix has its own power domain and more than 20 clock domains. Here I have already 25 clock domains. So the clock can be turned off for inactive blocks and kept only for the active ones. In order to apply this dynamic power reduction technique, we use hardware autoclock gating technique. In addition, when the whole subsystem is inactive, we apply the power gating and cut the static power consumption. So in order to simplify the functional model development, we have created an AXI initiator and target interface modules, which are based on TLM sample sockets and contain some register and extension mechanism, allowing the functional system C module to consider only the information relevant for the behavioral description. We have also created skeletons, simplifying a new IP modeling and protocol swapping. Realistic test bench. We have also created realistic test benches. We have developed several generic configurable traffic generator and some application-specific ones. So in this study, we analyze memory accesses, and in order to do this analysis, we need a memory model, an accurate memory model already to do this study. So it has already proven that PowerClock Arc and open source DRAM power tool can be used in a single framework, and to obtain an accurate estimate of the power consumption of a given DRAM memory, taking into account all the operation of the DRAM. So we did in this study 2 tests, one with simple memory model and one using the DRAM power model of the memory. The connection between the DRAM power tool and PowerClock Arc has been established in such a way we obtain the most accurate power consumption values while maintaining the simulation speed. For this purpose, DRAM power is invoked by the system CTLM model only once per read-write transaction window. So here in our case, we have a window of 10 transactions. So it then returns the value consumed by the memory for this window and update the overall power consumption computed by PowerClock Arc. So we have also enhanced DRAM power tool to calculate the average response time per transaction for each window in order to improve the functional model timing accuracy of our model. So here we plot some results of our simulation, and we have applied the clock power intent that I have described and defined the power management strategy on our model, and we have tested multiple use cases. In this one, we have only one active application-specific traffic generator that executes 256 kilobytes DRAM read accesses performed by the CPU cluster. Each data accesses is 16 bytes, and we consider sequential memory accesses. In order to optimize the memory usage, we apply 4K interleaving between our two DRAM memory systems. On this slide, we can observe the constant activity due to the continuous memory accesses, and the spikes here comes from the interleaving between the two memories. The simulation with DRAM power ignores some of the spikes due to the interleaving because we use windows of transaction, and the memory power consumption is normalized for the whole window. The correlation between the simulation results and the silicon measurement showed a very promised estimation already. We are about 95% of correlation with the silicon measurement. Now I would like to look at this use case where we consider an HD display and we execute one frame of transactions. The data paths are 256 bits and each pixel is 32 bits, so we have 8 pixels per transaction. We have a total of 259,200 transactions for one frame, and we consider multiple lines of prefetching mechanism, the horizontal and vertical banking period, pixel frequency, and the refresh rate. During the display traffic, the generator periodically sends bursts of transaction, which is the catching lines, and there are certain moments of inactivity between these bursts. Once again, the spikes comes from the interleaving between the two memories. The power consumption correlation of this use case is less precise, and comparing from the previous use case. And this should be due to the supplementary IP activity during real display refresh. But even with this abstraction, we have about 90% correlation and 90% accuracy for this more complex use case. So here we put an overview of the power consumption correlation, which includes the approximate value of generic multitask use case used for calibration here. And the memory copy and the display refresh use cases. The accuracy of the switch matrix activity is less or a bit lower than the one with DRSA module, and this is due to the additional use of the switch matrix by the peripherals during execution, which was not taken into account in the System C functional model implementation. Okay, so to summarize, the purpose of this study is to present a proof of concept of high-level timing-aware power estimation library called PowerClockArc on an AT System C TLM 2.0 of a model of NXP IP and its compatibility with an accurate DRAM model provided by the DRAM power tool. So the power consumption estimation accuracy is very satisfying, and at this level of abstraction, of course, with elaboration and the improvement of functional model, the accuracy of the power model is increasing. During the functional model development, PowerClockArc also helped us to detect some behavioral issues and to fix them. The collaboration with industrials helped a lot to improve the tool and to detect and fix problems that was not found during our simple academical testing previously done in last years. It also gave feedback on what can be added and improved in the methodology. So for more information about the PowerClock-ARC library tool, you can contact François Védier. The email is on the bottom of this slide. Or if you have question, I can answer your question right now. So thank you for listening. I hope I was clear, and if there is any question, I will pleasure to answer. Also, Antonio Genov can join us in the question and answer session for more details. Thank you.
So Amal, thank you again for your presentation. So, yep, are there more questions? So, okay, so Jakob is asking questions, so I will read it again. So, do you need to modify the functional models to enable the power estimation?
Yeah. Not modify in terms of modifying the functional model. We need to answer some code related to the power model in order to make the connection between the two models. But we don't have to modify the functional model in terms of modifying it.
And can you access like states from the functional model? So you are basically establishing a link to the power model to access some internal states of the functional model. Is this correct?
I didn't get the question.
So how do you solve technically the problem? So you're saying you're not modifying the functional model. So how do you establish the link between the power model and the functional model? I think maybe it was. Yeah.
As I said, it's the connection between the functional model and the power model already done by the design element, which is a reference on the functional module, so the IP itself, so the functional model of the IP. All the connection, all the computation is done on the design element module class. And also we have the PMU, which is a block of systemcTLM, which is inserted in the functional architecture and which it's connected directly with the power model.
Okay.
So the states, all the states are described in tables. We have NOPP tables, a PST table, and clock state table. As Antonio said, he just presenting, I think, the 3 tables. So we define the states, and then in the functional model, we request to move from state to another state.
Yep. So Jakob's question regarding this is whether the power model state pulls the state of the functional model, or does the functional model call the power model to report activity? So is there some polling or
already
reporting?
If I get the question, we have the 2 connections. We have connection from the power model to the functional model in order to act on the functional model if, for example, we are clock gated. But we have also the connection from the functional model to the power model. So it's a loop connection.
Okay. So are there further questions? So Jakob asks, who calls whom in the code?
Sorry?
Who calls who in the code is the question. Which one
code?
is
Which code?
in the code?
Which
yeah,
code?
I think between functional model and power model.
Yeah, I mean, actually.
Yeah, for sure.
Yeah, so just to be clear, I mean, my question is basically, I mean, you have this power model, right? And you have this functional model, and they're running side by side. So how do you actually get the, how does the power model extract the current state from the functional models? I mean, does it go around reading off some variables, or do the power models, send a call to, the functional model send a call to the power model saying, look, I just changed my state to something. So who's driving that? I mean, do you drive this like periodically, like, you sample
Not periodically. Actually, if a functional model, if you have a change on the functional model, for example, I will have a memory accesses. So I will ask the processor will ask, or the master, to turn the DRAM, for example, on active state, and then there is an update of the power computation done on these state changes.
Okay, so the function models report changes to the power model.
Yeah, for sure.
Okay.
Okay. So, are there further questions?
Yeah, maybe Antonio has. You want to comment on this question?
Yes, Jacob, for your question. So what we did for our modeling approach in NXP, we created a master module that will be the only functional module communicating with the power management unit. And the master module will take informations from traffic generators, and based on these informations, he can change the states using the OPP table. And like in our interconnect, the automatic log gating is activated. There is also a way to change the states directly from there. That is what we are doing in our use case. The states are changed directly from the functional models with the base with one base method used inside. And we can define different states. We can define different activity factors, etc.
Different techniques also, because here in our case we have auto clock gating, so it's automatically clock gated, the IP.
Hope we answered the question.